My name does begin with a B, but it's not Ben, it's Barry, I'm afraid. Sorry, man. Cool.
It's your apology.
I'm currently working as a software architect at Allen Gray, and today I just want to share with you kind of some of our experiences with introducing Go into our microservices ecosystem. Okay, so a lot of the discussion and the hot topics around microservices these days is around kind of container orchestration, observability, service meshes, so how to manage your entire ecosystem from deployment through to orchestration through to metrics and monitoring. There's not a huge amount of discussion around what language or ecosystem is a good fit for the individual microservices themselves. And that's probably because you can write a microservice in any language, right? Whether you're a startup or an established company, you're most likely to run with whatever skill set you have available to you. But that's not to say that certain languages aren't a better fit than others. And what I'd like to present you with today is how through our experience with using Go at Allen Gray, we found it to be an excellent fit for microservices. But not only that, but it has also kind of encouraged a simpler way of thinking about coding on microservices and kind of coding in general. Okay, so when we think of microservices, how big or small do we think they should be? Well, they should be as small as possible, right? But as big as necessary to represent the domain concept it owns. And this will obviously vary depending on your domain. But as a piece of software, we don't really think of them as large, sprawling pieces of software. They're kind of like the single responsibility principle as applied to an architecture. And at Allen Gray, over the last 3 to 4 years, we've been slowly building out a microservices architecture. Initially, we packaged them as Debians. We used Ansible. We deployed them straight onto the servers. But as container orchestration technology has matured, we've since moved on to Kubernetes. So at this point in time, this is what our system looked like. The vast majority of our APIs are written in Scala. We have a fledgling data science team who are using Python. And we also have some node gateways that we use for API aggregation and that kind of thing. So the issue here is that our readiness or health check endpoint is way too simple. We had a simple HTTP ping endpoint, return with a 200, and the service is good to go. But this doesn't really give any kind of indication as to whether that API's dependencies itself are down. So what we wanted is a solution that would allow each API to define its dependencies and what it means for it to be up or down and to receive traffic. So what are our options? Well, the first basic solution you would think of is maybe, let's create a shared library, okay? Let's create a shared library that understands how to test each of our different types of dependencies. We'll package that, we'll publish a version, then each API can consume that version. There's 2 issues with that for us. We currently have 3 languages. We don't want to create 3 separate libraries doing this exactly the same thing and publish them. And also we may have more languages coming along down the line, but we also felt the pain of distributed binaries in a microservice ecosystem. When we originally started out, we had one mega shared lib, and it just turned out that we were essentially creating a distributed monolith in reality. So we want that separation. Okay, what other options are there for us then for this solution? We decided to look at trying to solve our microservices problem with a microservices solution, and that is the Sidecar Pattern. So if you haven't heard the Sidecar Pattern, it's an API that lives alongside your primary API. Its lifespan is the lifespan of the primary API, and it also provides some kind of auxiliary functionality. Okay, so often it'll be logging or metrics. In our case, dependency management. Okay, so you'll have one sidecar, and it will be the readiness check. So configuration will come from your primary API at startup. And what's really nice about this is that it's in no way invasive to the primary API. And in a Kubernetes system, this works really well because you can deploy them together as a pod. Okay, so at the time, we kind of had internal conversations around maybe trying to find a language that was a little better suited to the microservices ecosystem than Scala and the JVM. Okay, so initially our basic sidecar requirements were low resource usage. We've got something like 80 APIs, 2 instances across 5 environments, say. That's a lot of additional APIs just to give us some observability and management into each API's dependencies. It'd be great if it had fast startup time. We don't want our sidecar to be taking 30 seconds to a minute to start up when our primary API is spinning up in 5 seconds. And whatever we choose, we'd like it to be microservice friendly. So what do we get out of the box in terms of microservices? Do we have to go choosing our different servers? Do we have to go choosing HTTP clients? You know, as much out of the box as possible. And in terms of general language requirements, I mean, these are the things you'd look at, you know, when you look at a language, any language you want to choose. So, strong community. How long has the language been around? Who's backing it? What large pieces of software are available? What's the community in terms of, you know, things like the TIOB index or Stack Overflow questions? Just kind of general stuff like that. Low barrier to entry. So this comes from, I guess, the pains of using Scala. So Scala is quite a vast language. It's got a lot of functional components. It's got OO as well, and the libraries are deep. Okay, it gives you a lot, and we want something maybe a little bit lower barrier to entry for people to get started with. Good tooling. How is it build tooling, test tooling, all of that kind of common stuff, and static typing. That wasn't a hard requirement, but historically in the company, most developers would have most experience with static and compiled languages. And as well as that, we want the performance and the type safety of a compiled language. So we kind of whittled down our list of languages that we wanted to choose from. So the first 3 are languages that already existed within our own ecosystem. Scala and Java, we've already eliminated. Barrier to entry is quite high. Resource usage for the JVM is certainly quite high in a microservices environment. JavaScript and Node. JavaScript is a Node. Node is not particularly good at CPU-bound activity, and as a financial services company, we would want a general purpose language that would at least give us some kind of number crunching power. It's not typed. You can use TypeScript or something like that to get around that, but it's also not compiled, so performance was an issue there. Python, out of the box, you don't really get a lot in terms of microservices with Python, okay? It's in general benchmark performances. It doesn't perform very well against compiled languages. C or C++, way too low level, barrier to entry way too high. Extremely performant, obviously, but as a general purpose language, not really a good fit for us. Rust would have been kind of the closest choice for us. A few things, though, at the time was a little bit immature compared to adoption. Go was much higher. Memory management, you know, we want garbage collection. So the barrier to entry is a little bit higher there. So in the end, after whittling down our shortlist, we decided that we would write our sidecar in Go. Okay. So some of the high-level design goals of Go are to try and approach the performance of C as a general language. It's intended to be fast, so it must take at most a few seconds to build a large executable, and it should be easy to program in. So, you know, very, very simple language constructs. But there was one design goal that was really kept in mind when designing Go, and this really shines through the more you use the language and get into the ecosystem, and that's simplicity. So Rob Pike is one of the co-creators of Go, and these are 2 quotes from him. It's, "Code is harder to understand simply because it is using a more complex language, and it's preferable to have just one way or at least fewer simpler ways of doing things." So Go is a language, its feature set is relatively small, okay? It doesn't give you a massive amount of data structures to work with. It doesn't have classical OO. It doesn't have things like, it doesn't have things like exception handling, classic kind of throwing and catching exceptions. But why is it designed this way? What's the goal? So it's simple, okay, that's great. So the thinking is that the less ways to do things with less features gives you more consistency, better readability, and more reliability. So less features means that in consistency space, 2 developers are most likely to use the same data structures, the same technique, to actually write something in a similar way. It's often cited that developers spend a lot more time reading code than writing code. I've seen stats of 10 to 1, but it's actually really hard to find good statistics on that out there. but through experience, I know that to be the case. So it's important that code is readable. You spend a lot of time reading code. And this, in turn, will lead to more reliability, okay? So this is kind of a good thing because as humans, we don't like too much choice, okay? So there's a book that came out in 2004 by a psychologist called Barry Schwartz, and it's called The Paradox of Choice, Why More is Less. And the premise of his book is that as humans, as consumers, too much choice is bad for us. It causes anxiety, it causes procrastination. If you are looking at two products and they're extremely similar and you end up choosing one, there's a very good chance that you're going to end up with buyer's remorse. So I think this is a really good analogy for the thinking behind the design of Go as a language. I would also argue that reducing choice is good, but for trivial things, actually eliminating choice is also a really good thing. And one of my favorite features, it's very, very minor in Go, is something called Go format. So all of the standard library in Go is formatted in a Go standard way. There's a command called Go format that will format your code in a Go standardized way. The vast majority of the code you see out there written in Go will be formatted in Go standard format. So this eliminates the need for things like Scala style or ESLint. All the code looks the same. I personally don't really want to spend my time in meetings with other senior engineers trying to choose what linting rules we want, arguing with somebody who feels strongly that a dangling comma after the last entry in our array is like something he feels really strongly about. So you can just use this, you can move on with your life and focus on more important things as an organization, which is quite cool. Okay, so I'll give you another very simple example of choices. So in Scala, these are some of the ways that you can loop over a basic array. Okay, so the first example there is just looping over your array and getting the index. There's another for loop which will give you the index. You've got a standard for loop which will give you the element. You can have a guard which says, hey, give me all my elements, but only ones that start with devconf. You've got a for each. You've got a zip with index, which will give you the element and the index. You've got a for with zip with index, and you've got a zip with index, a zip with stream from 1, which will start your indexing at 1. For loops also can be syntactic sugar for things like map under the hood, so it's quite important in Scala to know what's going on. I haven't even listed any of the kind of immutable loop structures such as flat map, map fold, and all of that comes in Scala. So there's quite a lot there in Scala for such a simple procedure. In Go, you've kind of two ways. The first one is the standard way that you can do in any language, pretty much just a for loop, looping over the index. The second is a range. So in Go, you can loop over an array, a map, a string, and something called a channel as well, using the range function. So this is pretty much standard idiomatic Go just for doing a loop. You'll pretty much, anytime you're looping, you'll use this standard syntax. It's consistent. If you're not interested in index or element, you just use an underscore there, and you can move on. Okay, so that's kind of simple basics. We're showing that Go is a simple language. But what about kind of more higher order parts of the language that allow us to compose our language? So Rob Pike again, the co-creator. If C++ and Java are about type hierarchies and the taxonomy of types, Go is about composition. So Go doesn't have classical object orientation, as I mentioned. It features heavily in composition. You can do interface composition. You can do struct composition. When I think of OO, I think of kind of design patterns, okay? So that classic Gang of 4 design pattern book that came out in, I think it's 1994, so it's 25 years old. So design patterns are great, and they've given us a shared language. They've given us patterns to solve common problems. And if you come from kind of the monolithic or the kind of enterprise background, you'll certainly be familiar with these. And I guess I've seen these in practice and through experience bleeding over heavily into kind of the microservice world. So sometimes microservices can be a slightly different beast. In your microservice range, you'll have auxiliary microservices, intermediate ones. You'll have ones that contain your business logic. Sometimes writing a microservice or designing for maintenance may not be a concern depending on what type of service it is. You may find that you write a microservice and it sits there for a couple of years untouched in terms of its business logic. So I think something to keep in mind and something that Go pushes is, do we need abstractions for the sake of abstractions? You know, do we need a factory when the object creation is simple? Do we need builder patterns? It doesn't come with those kind of because it doesn't have the classical OO idioms. Okay, so I was talking about how Go doesn't have the concepts of kind of traditional OO. It favors composition in interface composition and struct composition. So this is a fairly well-known software development idiom, and it's prefer composition over inheritance. And why is that the case? Well, composition tends to be a simpler mental model for humans. When we think of composition, you know, we look at a chair, we don't think that this is like an abstract piece of furniture of type chair, maybe of type office chair with a headrest. You'll just look at the chair and you'll think there's a chair and it's composed of arms, a seat, and a headrest. So I think the composition mental model is certainly simpler. We kind of build up larger objects from smaller pieces of objects. It's more of kind of a real world representation. As well as that, with classical inheritance, the mental model for deeply nested inheritance chains can be quite difficult. You can make changes to a base class and inadvertently cause issues for subclasses without knowing it. At compile time, it's fixed. One thing about composition is at runtime you can swap out different implementations, so that gives you a lot more flexibility as well. Cool, so very simple example of classical OO with, this is from Spring AMQP. It's a simple message listen container, you know, extends from abstract and then from Rabbit. So Spring is like a really good example of OO usage. You've got lots of different types of implementations. Because it's a framework, you've got lots of different choices you can make in terms of implementations. You can also write your own implementations. But the key takeaway here is that it's a framework and OO is well suited to that type of library, whereas what we want to build are microservices. Interfaces are quite unique in Go. This is something I hadn't seen before in a language. So you don't explicitly extend from an interface in Go. It's implicit. So it's kind of like duck typing, but it's checked at compile time. So it's a bit weird. If we define a simple printer interface with a function signature print string s, and we define a struct with that method signature, then the standard out printer is implicitly a printer. So that's quite powerful. We don't explicitly state that it is of that type. And what's interesting about this is that we could take a piece of code we wrote a year ago and we can retrofit it with an interface. We can create an interface for it. We could take a third-party library that isn't exported with an interface and we can write our own to fit that. So it's super flexible. And in terms of composition, it's really, really simple. This is taken from the Go core library. We've got a reader interface with the simple read method, a writer with a simple write, and to create a new interface type, we simply compose those two. Super flexible. You know, composition, smaller pieces, building. So I've talked about kind of the simplicity of Go. I've talked about some of the constructs, composition over inheritance, but the premise of this talk is about microservices. So what does Go give us in terms of microservices? Well, let's talk a little bit about kind of the anatomy of a basic microservice, and leaving asynchronous or event-driven stuff aside, let's take a look at the synchronous side. So generally it'll be over REST, it'll be over HTTP, so you'll want a HTTP server. You'll want something that can receive HTTP requests and respond accordingly. You want some way to parse that path. If you're in the RESTful world and you're representing your resources using the path, you'll want some way to parse that. You'll want some kind of data serialization mechanism. Okay, you're posting data in, you're returning with data, say JSON or XML, and microservices don't live in isolation. So you'll want some kind of HTTP client to make requests to third-party APIs, upstream APIs. You'll also might want to query a SQL-like database. So you may want some kind of common interface that allows you to do that. So Go provides all of these things out of the box in its core standard library. And one really nice thing about this is that you don't have to go searching for what you think is the best fit for your HTTP server. You get a battle-hardened, pretty well-designed HTTP server out of the box. Same for the HTTP client, same for your multiplexing or routing. So let's take a look at a pretty simple example of a server. It's just a little bit of code. So the imports, why am I showing you these? They're pretty much the most boring part of any software piece of code. Well, this is just to highlight how Go thinks about packages. So unlike kind of often with the Java or Scala world, where you end up with maybe 5 or 10 deep dot notation separated nested package names, in Go, the idiomatic way is to create it at one level. So highest level, simple level package name. So a lot of the core libraries you'll see are just like log, net HTTP, encoding JSON, encoding XML. Probably the most deeply nested you'll see is probably 3 deep in the core libraries. And I'll just talk you through a little bit of code as well. So this is just an example of a simple server that serves some JSON. So up the top, we've defined a struct, and a struct is just a simple collection of properties of a type. On the right-hand side, where you see the JSON, these are called tags. They're kind of like annotations. And what I'm specifying here is that when you serialize that, I want the title and the artist to be lowercase in my serialized JSON. Next, we have a song handler. So this method signature in Go is essentially any handler that has this signature can be used as a HTTP handler. So it'll be passed a response writer and a request, and obviously in there is where kind of your core logic lives. You simply create an array of songs with a single song. You create a new encoder, JSON encoder. We encode that, and we return it as JSON. And if there is an error, then we can return status internal server error. Next, we have a simple router. So out of the box, it gives you a simple multiplexer so that you can parse paths. And you can, if we receive a request on /songs, we can handle it using our songs handler. And at the bottom is the main entry point for any Go program. And there we simply listen on port 3000, start up a server. We pass it our multiplexer. So all of that is just serving a simple HTTP server. But it's all using just core library functionality. I didn't have to go looking for anything. I didn't have to pull in any dependencies, which is pretty nice. Okay, so to build and run that, Go format, my favorite command, Go build, and then we have our binary. So one really cool thing, and one thing that's often touted about Go is that it's really easy to deploy, because when you build it, it builds down to a native binary. So if you're on Linux, you'll simply get a native Linux binary, and if you're on Windows, you'll get an exe. To deploy that, we can simply, if we're in Docker, we'll simply copy that into our Docker image. We'll provide our environment variables, or whatever config we want, and that's pretty much it. It's really, really simple to deploy. Okay, cool. And out of the box, in terms of testing, you get 2 packages. The top one is a simple testing package, which allows you to define and run unit tests. So, functions of a particular signature. If you run Go test, it will pick those up. You can also get coverage out of the box as well, which is quite cool. The second is some HTTP test utilities. There's 2 things here that are quite nice. One is a HTTP response writer recorder. So if we go back to this example in our handler, we can pass the response writer recorder to our handler. It will record everything that we've done on it, whether it's a response body, an error status code, an error body, whatever it is. And afterwards, we can inspect that. So you can unit test your handlers very easily. It also provides quite a simple HTTP server running on localhost. You go http.server. It will give you a server running on whatever available port you can find. And then if you want to go http server.getClient, it will give you a HTTP client that will also make requests on that port. So for simple kind of end-to-end testing and basic tests, it's quite nice to have that out of the box. Yes.
CSS is strongly typed in JavaScript. It's quite elegant in terms of how it manages message distributions, JSON, and marshalling.
Okay.
What happens if the attribute or properties missing from JSON message and try to marshal it?
You can tell it to ignore it if you want. So like JavaScript, if you've defined an object and you serialize to that and the property isn't there, you can just tell it to ignore it. No, so Go has the concept of pointers, and also low-level primitives have default values. Okay, so if I were to return this object and I didn't set a string or an artist, it would actually return 2 empty strings for those values. If I define those strings as pointers, it would omit them completely because they'd be nil values in Go. But these tags give you a little bit of configuration as to how you want that to work. Yeah, so it's quite flexible. Okay, cool. Okay, so concurrency. So this is often touted as well as one of the major features of Go. Concurrency is obviously important when we're dealing with microservices. We want to be able to handle as many concurrent HTTP requests as possible, and we also want to be able to make downstream or upstream requests to databases or other APIs concurrently and aggregate those results. So Go has something called Goroutines, and you can kind of think of these as lightweight threads. The call stack starts at roughly 2 kilobytes. They're extremely small. They're extremely cheap to spin up. If you look at something like Java, where the minimum call stack will be created about 1 megabyte, you normally have to create pools, different types of thread pools, manage those life cycle of those pools. That's something that features less so in Go because it's so cheap to spin these up. If I just took a simple function called print, which prints the standard out, to run that concurrently, I would just prepend it with the Go keyword, and that would execute concurrently to the current Go routine that I have running. So how do you share memory essentially across these Go routines? Well, Go uses something called CSB. This is something that I'd kind of heard about before. I kind of vaguely knew about the term, but as I got into Go, it became more apparent how it worked and functioned. So it's called communicating sequential process. And the idea is that data is communicated between Go routines over a channel. And a channel is, I guess you can think of it as a pipe. Okay, you can have unidirectional, you can have bidirectional, and they're typed as well. So in the example here, creating a channel, I simply create an integer channel and assign it to a variable. So that channel is now kind of a first-class citizen. I can pass it around. I can pass it to functions. I can pass it to functions that are running concurrently in a separate Go routine. And then to read from a channel is this simple kind of arrow notation. And to write to a channel is also that simple write notation. And the reason this was chosen is it's designed to try and reduce issues around shared data like race conditions. It won't completely eliminate them. You'll need a little bit of a policy yourself as to how you use them, but it does give you quite a nice mental model to work with. It does also provide mutexes, so you can lock or synchronize data just like most other languages. And if you look at a lot of the core languages out there, and core libraries out there, mutexes are still used quite heavily, but this is kind of touted as the main way that you should be kind of communicating between Go routines. Okay, so we kind of initially said we wanted our sidecar to have low memory resource usage, or low resource usage in general. So we went ahead and we created our Go sidecar, and we put it in production. And we have a bunch of them now running in production. The smallest running production Scala API we have is running at 240 megabytes. The sidecar, on average, is about 20 megabytes. So its minimum is about 15 up to about 30. So resource usage is super low there, and that's a reduction of 12 times. I guess with our Scala APIs, certain things to note are that we're running Alpine base. We're running 64-bit version of Java. We want the kind of remote debugging tools, that type of thing. There are ways to reduce that. You can reduce it by going down to 32-bit if you want. You can do stuff like using ahead of time compilation as well, or class caching for faster startup. But using a JVM or a virtual machine, I don't think you're ever really going to get anywhere soon near kind of 20 megabytes. But this is probably not that fair a comparison because we have a sidecar, which functionality is kind of minimal, okay? And then we've got kind of a domain API. So we've written a couple of domain APIs in Go as well, and I tried to find two that were equivalent in terms of kind of the amount of requests they handled and the kind of functionality that they were both doing. So what I have here is a Grafana graph from one of our dashboards, and this is the Scala API. Okay, so the top 2 lines are 2 instances of the Scala API, and the bottom 2 are its sidecar. So on average, the Scala one's running at about 330 meg. The sidecar is pretty low. And if we take a look at one of our Go kind of, I guess, domain APIs, the average running here is probably about, what is that, 26 and a half megabytes. So it's kind of a massive reduction in memory consumption, which is a big win for us at the moment because we actually own and run our own hardware. We want to move to the cloud. We're waiting for the cloud providers to actually have data centers in Cape Town. Obviously, we have regulatory concerns that we have to think about. So even when we do move to the cloud, there will still be wins in that, even if we have on-demand capacity. So who cares? You know, memory's cheap these days. What does it matter? Well, I think there's still savings to be made. If we look at our 80 APIs, we've 2 instances, we've 5 environments, so we've got about 800 APIs running. If you look at the cost of maybe 16 gig of good quality server RAM, it's about 4.5 grand. I rounded up the previous Go API, it was 27 meg, let's just say it's running at 30 meg, all things being equal. The RAM for it would cost about 6, 7. If we look at that Scala API, the equivalent would cost about 76. If we double that for maybe disaster recovery, you're looking at 13 grand versus kind of whatever that is, 150 grand. So there are savings to be made, and I think as techies, there's something nice about like squeezing the most you can out of as little as you have. Okay, and what about the rest? CPU usage was something that was, I think it's much harder to gauge or kind of measure, particularly when the 2 APIs are running, they're doing different things at different times, there's other load on the servers. Looking at kind of in our environment, the CPU usage is roughly in line for the APIs that we've currently built with the JVM. So there's not huge wins there as far as we could see. That may change as we kind of flesh out our domain APIs and we write kind of more ones in Go that are taking on higher load and that kind of thing. Compilation in Go it's super quick. It's one of the goals was to have fast compilation in the order of seconds, and it is. Once you pull down your dependencies, it will compile extremely quickly. Like it's very impressive. And application startup also is super quick. I know it's not probably not a fair comparison because we're at 2 ends of the spectrum. We've kind of the JVM, and then we have something which is kind of at the native binary level. But with the JVM and Scala, you've obviously got the JVM spinning up, you have just-in-time compilation, you may have class loading. With a lot of the web applications, you've got annotations, you're going to have annotation scanning with things like Spring, you're going to have the wiring up of your application. So application startup can be quite slow in Java and JVM world. But in Go, it's super quick. Okay, Go, it's great. It offers a lot, but there will be things that you'll most likely miss coming from other languages. Generics is one, and there's a lot of discussion in the community about generics. As your code bases grow in Go, you will often have to repeat code, essentially, with types to get the effect of generics. Go is currently on version 1.1.2. There's a draft proposal for generics out for Go 2. I'm not sure yet if it's going to be added because the maintainers are super keen on keeping the language as simple as possible. It's one of the traits of the language. They don't want to compromise that, so it'll be interesting to see where that goes. Structured exception handling. So Go doesn't really have the concept of exceptions. You don't throw and catch exceptions. You actually return errors from functions. So functions, you'll often return 2 values with kind of the syntax being the first value is the one you want to return, and the second one being an error. And the idea being that when you return from the function, the caller has to handle it in place. Well, they should handle it in place. It's quite simplistic, and it can become quite repetitive. And for Go 2, there's also a draft proposal in to try and eliminate some of that kind of boilerplate that you have to go through when using that. And consistent package management. There's been a couple of attempts at decent package management solutions for Go. dep is one that a lot of people were using, which was kind of outside of the core library, but what they've decided to do now is bring that functionality of package management into the core libraries, into the core Go runtime. So there's something called Go module, which is in beta. And in version 1.13, the next version, that will be fixed. So they have come up with a solution. They brought it in-house, and that will be the way forward for package management, but previously it wasn't so hot. So there are things you'll miss, but I think as the community shouts out for what they miss, the maintainers listen, and where possible, they'll address these things, which is quite cool. Okay, so what about our original sidecar as a piece of software? How did that work out for us? So what we had on each sidecar is an endpoint that was scraped by Prometheus, time to use database, and then we would graph it on Grafana. So this is a very simple example of one of the APIs, and it's 3 dependencies. You've got 2 other APIs, and you've got a MS SQL database as well. If one of these goes down, you'll see it in red. In the history of it, you'll see it there as well. And what this allows us to do is alert on all of this kind of thing. It gives us quite a lot of visibility into the dependencies of an API and alerting on that as well, which is very, very cool. So currently, we have about 160 API sidecar instances running in production. So they've been there for 6 months to a year, humming along. No worries there, really solid. We've got about 20 domain APIs written in Go. So we kind of took the approach of, we picked off a few simpler auxiliary APIs, things that are not like core business functionality. And as we roll those out, we added our own kind of libraries and bits of functionality as we went. So we're also doing async. We're using AMQP. We're using Rabbit. So we found it to be really stable and really performant as well, the Go implementation of that, which is quite cool. A lot of our custom CI pipeline and deploy tooling are written in Go. We have a team called Delivery Engineering, which have written a lot of our kind of glue around our Kubernetes cluster. And Go is really an excellent language for kind of server language. And we're also pushing Go as a kind of a primary API development language. So in summary, I think without a doubt it's microservice friendly, okay? Out of the box, it gives you a lot. You'll most likely want to supplement some of those with third-party libraries like you would with any language, but you don't necessarily need to. Okay, less dependencies is good. Encourage simplicity. Simply because of the way the language is designed, it almost forces you to think a bit simpler about how you write your code. At times it can feel a little bit procedural. But certainly with Scala, for me, it makes it very, very easy for people to write extremely unreadable code. And with Go, it kind of forces you into a slightly simpler mode, so much more readable code. Barrier to entry is really important there as well, so we can get graduates in. Those guys can be up and running and productive really, really quickly, or any kind of junior developer, which is really cool, and start contributing early. And low resource usage. Certainly in terms of memory, we found it to be extremely low in resource usage, which is also a win. Okay, cool. That concludes my presentation. Thank you.
Thanks, Barry.
Cool.
Even with the delay, you're well on time. Any questions? At the back. Okay, so this is closer. I'll just start here.
I'm just wondering, like Java has a whole ecosystem of specs and implementations like JDBC, like JMS, that, because rarely does your API live in isolation and needs to talk to other stuff around it. How mature is Go in that regard? Like, will you be able to find database drivers for obscure databases? Will it integrate with Elastic or Mongo or things like that?
We use MongoDB. We use Couchbase for some things. We have MS SQL, we have Oracle. So we have stable drivers for all of those that are out there in the community. I guess like your JSE and JREs, those kind of specs, they're not out there for Go, right? They don't have that kind of specification that they publish, and then people write their implementations of that specification in that respect. Yeah. Okay.
Hello. I want to ask concepts around the functional nature of Scala. If you were using that, are you losing that? Does it come with that?
So Go, immutability is not like a concept that's baked into Go. Okay. A lot of the functionality that you would get in Scala isn't there, so you kind of manage that yourself. It does have concepts of kind of higher order functions, so you can assign a function to a variable. You can return functions from other functions. You can pass functions to functions. It certainly is that side of things, which is quite nice, but it doesn't have immutability baked into it. Yeah.
Okay, cool. Thank you.
Okay, last question.
What about nulls? Can you return null objects from functions?
Sorry, what about?
Nulls, null objects.
It has the concept of nil, which is essentially null, no value. One thing to be aware of is that, like I said, the primitives have default values, which is funny. So if you're not aware of that, the default for a string is an empty string. The default for a Boolean is false. Default for an int is 0. So sometimes returning something that you don't think has a value may return a value. Yeah. I think there's one more question down here.
One more, okay.
Yeah.
As a more senior dev, in fact, as an architect, can you see the difference between grads who have to write code and Go initially, and in terms of how they reason about the solutions you build, as opposed to those who had to start in Scala, in terms of getting to the product and being able to reason about why it should work or what works with it and what they need to deliver?
I suppose we've been running for Go for about a year, so we have had some grads in the last 6 months. Certainly, the amount you need to learn to get up and running with Go is a lot less, for sure. The language features and constructs, they're pretty minimal, right? You've got arrays and slices and maps. Under the hood, it doesn't really have tree sets or various data structures. And there's a lot less ways to do the same thing as I showed you with the looping. So I think in that respect, it's much easier for someone not familiar with the language to get into it, whether they're a grad or an experienced developer. Whereas Scala's, it's quite a vast language. I think if you don't know what's going on under the hood, and you don't know really the details of how you're working in Scala, you can get yourself into a bit of a mess. Yeah, it's pretty vast as a language. Yeah, I hope that answers your question. Kind of. I don't like the grads have been working on both. We have grads who work on both Scala and Go at the moment. So I don't have any feedback from them at the moment personally as to which they find kind of easier to get into or more productive in. Okay.
Is a simpler programming language? Is it that when they go on, they're able to reason better about what my requirements are, what do I need to deliver, what are my dependencies, why is what I'm doing valuable, as opposed to someone who maybe started in Scala and has to reason differently because they have different environments?
You would probably reason differently. Once you have OO as a tool, for a lot of people, if that's what they learned in college, that's going to be their go-to. And often that may be unnecessary depending on the size of the piece of software you're developing, whereas the composition side of Go really kind of lends itself to thinking simply initially and trying to build bigger pieces with your smaller parts. Yeah, that's...
Excellent. Okay, can we... Barry will be available in the panel area afterwards, after lunch.
After.
After. So, excellent. Can we give some a round of applause? Thanks very much, Eric.
Thank you.